Hello everybody, today we'll talk about supersonic Doppler effect. So the Doppler effect or Doppler shift is the apparent change in frequency of sound when there is relative motion between source and the observer. Austrian physicist Christian Doppler described this in 1842. The perceived frequency can be greater, less, or stay the same based on different cases, and it's applicable both to sound waves and light waves, but we're going to talk more about sound waves. In this case, we're going to talk about the supersonic Doppler effect. That means the Doppler effect that occurs when the source of sound is traveling faster than the speed of sound. If you want to learn more about the general Doppler effect, that is when the speed is very less compared to the speed of sound, or the sonic Doppler effect, you can check the link in the description below. So the speed of sound is the distance traveled by sound in unit time as it propagates through a medium. The speed of sound is 343 meters per second at a temperature of 20 degrees C in air. Now, in order to break the sound barrier, one has to travel faster than sound can travel in the medium of interest. So, for example, in air, if you want to break the sonic barrier, you have to travel faster than 343 meters per second or whatever speed sound travels in air at that temperature. So, if an airplane travels at 686 meters per second, which is twice the speed of sound, so it's said to travel at Mach 2. So this is the equation that relates the apparent and the original frequency. So F is the apparent frequency, F0 is the original frequency, C is the speed of sound, V0 and Vs are the velocity of observer and source respectively. So we'll use this equation and we'll develop different cases, especially when the source of sound is traveling faster than the speed of sound. So here's the setup. So there is an airplane on the left and there is an airplane on the right. So the airplane on the left is moving toward the right, and we'll have two cases in this situation. And here's the important thing: the airplane is moving at Mach 2, which is twice the speed of sound. And there's a stationary observer on the road, and let's see how he registers the sound emitted by the airplane. So the case one is the source is moving toward the stationary observer on the road, and the source is traveling at twice the speed of sound, whereas the observer is stationary, so his velocity is 0. So if you plug in, this is what you get. F, or the apparent frequency, is negative of the original frequency. So what does this mean? Let's think in detail. First of all, when I say negative, so it means direction. So let's say we say that I'm moving at a velocity of -5 meters per second. So it means that I'm actually going backwards. So if you're in a car and if you say I'm going at -5, so it means that you're taking reverse. So the negative actually implies your direction of travel, and the magnitude says how fast you're going. So let's apply the same concept here. So if frequency is negative, it means time is also negative. So if you simply say time is negative, it means that you're hearing the past. It is somehow related here. So what it means is there is no sound waves to hear initially, because the source of sound, or the plane that emits sound, is actually traveling faster than the speed of sound. Well, like way faster, 2 times faster. So if you're the observer, you'll be able to see the plane, but you'll not be able to hear anything. You will hear after a delay. So after the plane has passed by, and then you will be hearing the sound. Now you need to note that the sound that you're hearing is not instantaneous. It's actually the past. Past because the plane emitted sound at one point, and then the sound waves are still following to reach you because the plane is way faster. So what you're hearing is the sound emitted by the plane at a time, like in the past. So when you're not hearing it instantaneously, and hence it's negative, and hence the frequency is also negative. So the second case is simpler. It's just that the source is moving away from the stationary observer. It's still traveling at twice the speed of sound. So if you plug in those values, you get 1/3. So the apparent frequency is just 1/3 of the original frequency. So here's the second setup. This setup involves the plane being the observer, whereas the source is stationary, for example, a factory to industry emitting sound waves. So we're going to see how the observer in the plane, who's traveling at Mach 2, is going to register the sounds when he's coming toward the source and when he's receding away from the source. So the first case is the observer and the plane is moving toward the stationary source. The source is stationary, so the velocity is 0, whereas the observer's velocity is twice the speed of sound, or Mach 2. So if you plug in those equations, you get the apparent frequency registered by the observer in the plane is thrice the original frequency. This is because of the velocity of the observer. And the next case is the observer is moving away from the stationary source. So the source velocity 0, the observer is still 2c. So if you plug in this equation, you get the apparent frequency is negative of the original frequency. But in this case, the negative value has a different meaning. It's just that the sound waves generated by the source, which is stationary, are not fast enough to catch up with the observer, who is traveling faster than the speed of sound. So the airplane or the observer is traveling at twice the speed of sound, whereas the factory that's emitting the sound waves is just traveling at 1 time the speed of sound. So it's like the sound waves want to catch up with the observer, but they will never succeed because their velocity is just half. The observer will be able to hear the source only when the source passes him. Now the source is stationary, it's not passing him. So, and also the observer is continuously moving at Mach 2, whereas the sound emitted by the source is only traveling at 1 time the speed of sound. So as the sound will never catch up with the observer, he will never hear anything. So he will hear it only when the source passes him. So the next setup is a little different. In this case, the observer is no longer stationary, but it's actually running toward the plane, whereas the plane is still traveling at Mach 2 from left to right. Let's see what happens, how the observer registers the sound. So in this case, both are moving toward each other. So the velocity of source is 2c, whereas the velocity of observer is non-zero, but very low compared to the velocity of the source. So if you plug those equations in, you're going to get the apparent frequency is approximately negative for the original frequency. It's because the velocity of the observer who's running, is not even comparable to the speed of the source, which is twice the speed of sound. So it's just the case is almost same as the previous case that we have seen where the observer was stationary instead of running. And the next case is again the same, but the source and observer are moving away from each other, but the observer is actually running. And if you plug those equations in, you can get the apparent frequency registered by the observers almost 1/3 of the original frequency. So the next setup is a little different. In this case, the source and observer both are, people in airplane, and they're both moving at the speed of Mach 2. Now let's see what happens, how the source and observer, what kind of cases this situation involves. So in this case, both are moving toward each other at supersonic speed or Mach 2, so their velocities are same. So you just plug in and you get the apparent frequency registered by the observer is -3 times the original frequency. So what does this mean? So the observer will be able to see the source, he can see it coming, but then will not hear anything because, you need to understand that both are traveling at Mach 2, which means both are emitting sound waves, but then they're traveling way ahead of their own sound waves. So the sound waves are still trailing the source. So this negative sign represents a delay. So the observer will register 3 times the frequency, but only after the source has passed. It's because they both will cross each other and they both will actually hear the plane emitted by their own, by the other plane sound, but only after this time has passed by. At that point, when they're going to be hearing the sound, it's like there will be nothing around, but they'll still hear the sound. So it's just a sound that was emitted, back in the past that they're hearing it. So the next case is again, they're moving away from each other, and you plug in the equations, you still get negative. It's because they are hearing the past and not the present. The next case is a trivial case because the source is chasing the observer and both are traveling at supersonic speeds. So you plug in the equation, you're going to get that the apparent frequency is same as the original frequency. There is no Doppler effect. It's because Doppler effect relies on the fact that there should be some relative motion between the source and the observer. In this case, both are moving at twice the speed of sound, but there's no relative motion between the two. It's like the relative motion between the two is 0, so there is no Doppler effect. So to conclude, the Doppler effect or Doppler shift is the apparent change in frequency of sound when there is a relative motion between the source of sound and the observer. And the apparent frequency can be same, different, negative, due to different conditions that we have seen. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.